Well, if we want to graph the tangent function, here's one big takeaway that I want to get out of that unit circle slide. The period is no longer 2 pi, but the period equals pi. It's a big takeaway here. This is one of the major differences between the sine and cosine functions. So what that means is if we want to establish our key intervals, we're still going to be dividing by 4, but this time our key intervals are going to be described with pi over 4 spaces in between my x values. So I'm going to fill out a table, and this time I'm going to start from negative pi, and I'm going to increase by by pi over 4 for each of my x values. So this is going to be negative 3 pi over 4. Then this will be negative pi over 2, negative pi over 4, then 0, pi over 4, pi over 2, 3 pi over 4, and pi. So now if I actually can go back and grab those tangent values from my unit circle a couple slides ago, I can fill that out with this table right here. So I'm going to go ahead and do that. I'm going to grab those values. So when the theta is negative pi, or when x is negative pi in this function, y equals tangent of x, the y value, or the output, will equal, the tangent will equal 0 when theta is negative pi. And then I'll have a positive 1 for negative 3 pi over 4. For negative pi over 2, I've got an undefined. For negative pi over 4, I have negative 1. For 0, I have 0. Then I have 1. Then I have undefined. Then I have negative 1, and then I have 0. All right, so let's plot these points and see what we're looking at here. I'm going to plot this in blue. So at negative pi, I'm at 0. Negative 3 pi over 4, I'm at positive 1. Undefined here at negative pi over 2. Negative pi over 4 is negative 1. Then 0. And then 1. Undefined. Negative 1, 0. All right, so what's going on here? Now, before you feel tempted to just connect all of these dots, there's something important going on with this undefined. When I have an undefined x value, that's the cause of that is a vertical asymptote. So I'm actually going to put vertical asymptotes in my graph at negative pi over 2, at pi over 2, and hopefully you can kind of see the pattern of this, how often this will happen. And this should happen every period length. So I'm actually going to put another one here at 3 pi over 2, another pi radians away, and I'll put another one over here at negative 3 pi over 2, another pi units away. So now what's actually going on here is if I can get a little bit more of a sense of what is occurring in between these asymptotes, I am increasing the whole time through between these asymptotes, and then I'm kind of just approaching this asymptote without actually crossing it. So what the graph will actually look like is something like this. That's what's going on in the very middle, and then that pattern will actually repeat. I'm going to add another point here since that pattern will continue. All right, so something very different from what we've seen before. This tangent graph does not continue up and down like a sine or a cosine, but it is still periodic. We still have these repeated patterns to what's going on here. So let's now talk about some of the properties. We've got the domain, the range, the period. Here's a little bit prettier of a graph. The domain is something a little bit different. It's not negative infinity to positive infinity because I have all these points where x is not defined. So I need another way to describe that. So here's one way that we can do that. The domain is that x, here's going to be some fancy notation. X is an element. It's kind of like an e. It's an epsilon. X is an element of the reals, or the real numbers. That's the fancy symbol for the real number set. And I'm going to say where, the colon represents the word where, x cannot equal. Now I need some sort of way to describe all of these asymptotes without, I can't list them out, right? I could be here forever. So I'm going to say x cannot equal pi over 2 times k. Now let me break down what that means. I'm not finished yet, but what I'm saying is that every interval, or every time I see a pi over 2, or some sort of pi over 2, I have an asymptote. Now this isn't going to be every pi over 2, because technically pi is 2 pi over 2. So I need some sort of way to say, as long as I have an odd number of pi's over 2, then I'll have an asymptote. So like 1 pi over 2, 3 pi over 2, 5 pi over 2. So what I can say here then is I've created this k, and I'm going to say k is an odd number. So this is a way to describe the entire domain for the tangent function. A little bit weird, but this sort of encapsulates what x can equal and what x cannot equal. And that's the whole purpose of writing a domain. For the range is a little bit easier. This is going to go on forever in the negative direction, forever in the positive direction. So this is going to be from negative infinity to infinity. Or another way you might see this is negative infinity to infinity with this type of interval notation. Both mean the same thing. The period we've established, that is the distance between asymptotes, and that's pi radians. It's also the same distance between my little center points here. Lots of different ways we can talk about this. All right, those are some of the general properties. As far as transforming this and stretching it and compressing it and moving it around, the patterns will typically be the same. But let's label some of the important things on this graph. So I've got some names for some of these points. The first one here is I'll talk about this middle point. The name of that is the inflection point. That is literally where I have a point of inflection. What that means is that I change concavity. So I'm changing here from concave down to concave up exactly at that point. That is what an inflection point is. I also call this like the starting point. And so in this case, for the regular function tangent of x, the starting point is at 0, 0. If I were to move this thing around, I would be using my shifts based upon this point 0, 0. I'd be moving at 0, 0 left and right. A couple other things. I've labeled these next key values as, I call these my anchor points, because they're like the next value that I need to include inside of my graph. I'm not going to graph infinity or negative infinity. I'm going to put an asymptote here. So I can graph, just like before, I want to get 5 points per period, and that way I can get a good sense of what this looks like. So I'm going to include these points one key interval over that I call the anchor points. And one thing that's important to note is that the distance from my midline to my anchor point is going to equal A. So this gives us that vertical distance from my midline to my anchor point. That's where the A value comes in here. So if I stretch this, I'm changing the distance between these 2 points. The period is still going to be affected by B, and this time it's going to be just pi over B rather than 2 pi over B. The C is still my phase shift, and the D is still my midline. So that much has not changed. If I were to look for asymptotes, I can find that by analyzing my phase shift as well, knowing that the asymptote will always be half a period after I begin my function. So this distance here, I guess what I'm illustrating here, is the distance between my starting point and my asymptote will always be 1/2 of the period away. All right, so that's some general pieces. In the next video, we're going to actually take a look at a function, a tangent function that has been transformed in some way, and we'll kind of break it down into its smaller parts and then graph it.